Let's look at the solutions of number system bytes. Find the number of composite odd natural numbers less than 100 and relatively prime to 63. If the number is relatively prime to 63, it should not have any multiple of 3. It should not have any multiple of 7. So the number thus created will not have 2, will not have 3, can have 5, will not have 7, can have 11, can have 13, can have whatever other prime numbers. So we simply have to see numbers less than 100 that can be composed of these prime numbers. The first number that we can see is 5 into 5. The next number is 5 into 11. Then you have 5 into 13, then 5 into 17, then 5 into 19. I cannot go to 5 into 23, that would be greater than 100. And even the next smallest grouping that you can see, 11 square, that wouldn't work because that is greater than 100. 11 into 13 is greater than 100. So the entire list of numbers is going to be this much only, which is 5. Next, when a 2-digit number having distinct digits is divided by the sum of its digits, gives the same remainder as when a 2-digit number that is formed by reversing the digits of the original number is divided by the sum of its digits. How many such 2-digit numbers are possible? Okay. So we are saying 10a plus b is k times of a plus b plus some remainder r. And we are also saying 10 times of b plus a, reverse of that number is m times of a plus b plus r. Now we don't know which is larger, k or m, which is larger, or 10a plus b is larger or 10b plus a is larger. But if I subtract the second expression from the first one, the second equation from the first equation, I would have 9a minus 9b is equal to k minus m into a plus b, or I would have k minus m equal to 9 times of a minus b by a plus b. Now k and m were supposed to be integers. So a plus b will completely divide 9 into a minus b. A plus b will completely divide 9 into a minus b. Now when it is completely dividing, can you see a plus b cannot be cancelled out by a minus b. A minus b cannot be a multiple of a plus b. So some part of a plus b has to be a factor of 9. Some part of a plus b has to be a factor of 9. So from here we can infer that a plus b has to be a multiple of 3, some multiple of 3. And given that these are single digits, given that these are single digits, a and b are individual natural number digits, all we have to do is check cases now. So let's say a plus b was equal to 3. Then I would have 9 by 3 a minus b. Cancel, I get 3 times of a minus b has to be an integer. So possibilities for a and b are going to be 2, 1 and 1, 2. Both these numbers would work. Let us check with a plus b is equal to 6. So I would have 9 times a minus b divided by 6. Cancel 2 times, cancel 3 times. So now a minus b has to be an even number. So let's look at the cases. I would have 1, 5, 2, 4, 3, 3 would not work because the question said distinct digits. 4, 2, and finally I would have 5, 1. These 4 cases would work. Let's check with a plus b is equal to 9. This is the simplest case. A minus b by a plus b, which I have taken as 9 in this case. So cancel, a minus b has to be an integer. So I will have all cases possible: 1, 8, 2, 7, 3, 6, 4, 5, 5, 4, and 6, 3, and 7, 2, and 8, 1. Okay. Now let me check. A plus b is equal to 12. A plus b is equal to 12. Then I would have 9 into a minus b by 12. Cancel 4, cancel 3. Now a minus b has to be a factor of 4. A minus b has to be a multiple of 4. So the cases that I can potentially see are single digit numbers, multiple of 4. So 5 minus 1 would work. and 5 minus 1 works. So 1 minus 5 would also work. Additionally, 9 minus 1 would work. 62 and 26 would also work. 62, 26 would work. 91, 19 would work. 8 ka difference. Can I get 8 ka difference in any other case? No. 73 and 37 would work. 73. Oh, I'm making a terrible mistake. No, I'm making a terrible mistake. I'm making sure that they are multiples of 4, but I'm not making sure that summation is 12. Summation is 12 and their difference is a multiple of 4. For one case would be 4 and 8. Another case would be 8 and 4. Sum is a multiple of 12. Difference is a multiple of 4. These are the only two cases possible. I'll make all the possible cases. 3 and 9 doesn't work. 4 and 8 counted. 5 and 7 doesn't work because the difference is not a multiple of 4. 6 and 6 not possible because distinct digits. Then 7 and 5 doesn't work. 8 and 4 already counted. 9 and 3 doesn't work. So yes, I only get 2 cases here. 2 cases here. 2 cases here. 4 cases here. 8 cases here. Altogether, I will get 16 cases. Moving on. Question 3. X is equal to 0. ABCD, ABCD, ABCD. First thing you should be able to see is X is equal to ABCD divided by 9999. Okay, such that A plus B plus C plus D is equal to 9K, which would mean ABCD is a multiple of 9. 9 into K by 9999. Okay, where K is a natural number and A plus C is equal to B plus D. A plus C is equal to B plus D. This in itself should tell you effectively what they are saying is ABCD is a multiple of 11 also. So now this will translate into 99 times M by 9999. What is the smallest natural number by which X should be multiplied to convert it to an integer? 99, I can cancel it out. 99 will go. I'm left with 101. So effectively X is equal to M by 101. So which is the smallest number X should be multiplied by to convert it to an integer? That number will be 101 itself. Next question. In a 5-digit number A, B, C, D, E, where A is less than 5. Okay, A, B, C, D, E. A is less than 5. So A can take values from 1 to 4. The leftmost digit is the average of all the digits of the number. Average of all the digits of the number. Okay. The digit at the hundreds place is the average of the digits at the hundreds, tens, and units place. And the digit at the tens place is the average of the digit at the tens place and the units place. Okay. This is a wonderful clue. Last one. The digit at the tens place is the average of the digit at the tens and the units place. Now see, if digit units place is E, if units place is E, and when I introduce a new digit, D plus E by 2 is equal to D, is what we've been told, or E is equal to D. This much we know. So basically it is not a 5-digit number with 5 distinct digits. I have a number like this. I have a number like this, A, B, C, E, E. Last 2 digits are same. Now working my way backwards, the digit at the hundreds place is the average of the digits at the hundreds, tens, and units place. So C is equal to C plus 2E by 3, which gives me C is equal to E as well. So essentially the number I'm dealing with is A, B, C, C, C. The last 3 digits are identical. We don't have any information about the thousands digit. We only know A is the average of these 4 digits. If A is the average of these 4 digits, A can take values from 1 to 4. So when A is equal to 1, B plus 3C should be equal to 4. So let's see what all possible cases we can get here. When C is 0, A is 4. When C is 1, B is 1. So we get 2 cases from here. When A is equal to 2, B plus 3C is equal to 8. C is 0, B is 8. C is 1, B is 5, C is 2, B is 2, and this is it. We cannot have any more cases. When A is equal to 3, B plus 3C should be equal to 12. Okay, C cannot be 0 now. When C is 1, B is 9. When C is 2, B is 6. When C is 3, B is 3. And we can't have any more cases. This is also done. Finally, we have when A is equal to 4, B plus 3C should be equal to 16. Can C be equal to 0? No. Can C be equal to 1? No. Can C be equal to 2? No. Can C be equal to 3? Yes. When C is equal to 3, B is equal to 7. When C is equal to 4, B is equal to 4. When C is equal to 5, B is equal to 1. And this is the entire list of possible cases that we can have. So we have 3 cases here. We have 3 cases here. We have 2 cases here. We have 3 cases here. Altogether, how many cases are we getting? We are getting 11 cases. Let me just make sure the numbers that I have come up with are fine. 14000, 11111, cool. Then I have 28000. Then I have 25111. Then I have 22222. Okay. Then I have 39111. Then I have 36222. Then I have 33333. Then I have 47333. Okay. Then I have 44444, and I have 41555. The last 4 digits should add up to 16 in these 3 cases. Yes. The last 4 digits should add up to 12 in these cases. Yes. The last 4 digits should add up to 8 here. Yes. The last 4 digits should add up to 4 here. Yes. This should be the right answer. How many such numbers are possible? There are 11 such numbers which are possible in this case. Okay. Have I missed out on any number? Let me check. Oh, I have missed out on one case. I have missed out on one case here. 0 and 4 here. I can have a case of 0 and 4 here, which would give me 30444. One such number is still excluded, so answer will not be 11. Answer will be 12. Last question. How many 2-digit natural numbers AB are there such that the value of A by B is not an integer, where A and B are single-digit natural numbers? Okay, A and B are single-digit natural numbers. So any number divided by 1, when B is equal to 1, any number divided by 1 will give me an integral result. So this is not valid. When B is equal to 2, I need odd numbers at the top. There are 9 potential numbers at the top, 1 to 9. From those, I have to remove all the even numbers. So I get 5 cases here. Those 5 cases being 1, 3, 5, 7, and 9. We don't get an integer here. When B is equal to 3, I have to remove all multiples of 3. So 3, 6, 9 will go. I will get 6 cases here. When B is equal to 4, I have to remove multiples of 4. So 4 and 8 gone. Something divided by 4, I'll get 7 cases here. Something divided by 5 is happening. When B is equal to 5, something divided by 5 is happening. I will get happily how many cases? 8 cases. Apart from 5, everything else works in the numerator. When B is equal to 6, something by 6, again 8 cases. When B is equal to 7, something divided by 7, again 8 cases. When B is equal to 8, something divided by 8, 8 cases. And when B is equal to 9, something divided by 9, again 8 cases. So how many cases do we get? 8, 8, 8, 8, 40 from here. And then 5, 6, 7, 18 more. Altogether, we will get 58 cases. That will be all for this episode. Hopefully, you learned about the merits of counting cases slowly. Okay, bye.